Hello, and welcome to this is lecture 5. We'll be beginning the discussion on defects in crystals, in the crystal structure of metals, which are kind of key in engineering their properties or enhancing their properties. So, when you talk about a defect, typically it has sort of a negative connotation. In this case, it just means a variation or a change or an absence of this long-term three-dimensional order in the atoms. And because that it's not perfectly lined up in 3 dimensions, those defects, those ways in which it isn't consistent, are the key aspects of metals that we can employ in making metals stronger. And those defects come in kind of 3 groups. The first group are point defects, one-dimensional defects. And there's 2 different kinds of those. One is a vacancy, meaning that's just a place where there would be an atom and it's not there. And then the second kind of point defect is an impurity atom, or what we might call a solute atom. So this is not the same as the host metal. It's sitting at the site where a host metal would be, or in between the positions of the host metal. Then the 2-dimensional defect is called a dislocation. I'm not going to talk about it much today. We'll get into it down the road. But those defects are what we use when we strain, harden, or cold work metals. And then the 3D defects are grain boundaries. These are surfaces across which the direction of the crystal changes. And we can add those defects and make a metal stronger by a process that's called recrystallization. So the first kind of point defect that we'll talk about is the vacancy. I started to speak about this in the afternoon section. Like I said, it's a place where there would be the solvent atom, but there's just nothing there. And as temperature increases, the number of the vacancies increase. So if I have a certain number of atoms, and at like absolute 0, there's no vacancies. So there'll be a certain number of unit cells. That all of the atoms that I have fall into. But as the metal is heated, there's an increase in these numbers of locations where there isn't an atom. So if we add heat, we're going to have to add unit cells to accommodate those atoms. And if we add unit cells, then we're increasing the volume. So this increase in temperature that causes vacancies to increase is the coefficient of thermal expansion. That's where that comes from. Now, in order to calculate the number of vacancies at a specific temperature, there's 2 steps involved. The first step is to calculate the number of places that there could be an atom total. And then we use an equation to take that number and determine how many of those sites are vacant. So to calculate the number of lattice sites, and this is in per unit volume. So I know density will give me atoms per unit volume. So if I take density, and that'll be in grams per we could put it into per cubic meter. Now I have grams per cubic meter, but I need atoms per cubic meter. So I could take 1 over the atomic weight, which is in grams per mole, and then I just multiply by Avogadro's number, atoms per mole. And now I'm going to have the grams cancel, the moles cancel. I'm going to have atoms per cubic meter, or lattice positions per cubic meter. So we might call that density times Avogadro's number over molecular weight. Once we have that number, then the number of vacancies is a fraction of that, and we use what's called an Arrhenius function to calculate that. So n sub v is the number of vacancies. That's what we're trying to get. And n is what I just calculated, the number of atoms or the number of lattice sites. And we get that by taking the exponent to the minus q sub v over kt, where q sub v is the activation energy, which is either given or you're calculating it in electron volts per atom. K is Boltzmann's constant. We're going to use electron volts when we solve the problems. So we use Boltzmann's constant, 8.62, 10 times 10 to the negative 5 electron volts per atom, degree Kelvin. So T, temperature, is in degrees Kelvin. So here's an example of using that. We're given temperature at 1,000 C, so that would be 1,273 Kelvin. The activation energy, the form of vacancy in copper, there's Q sub V, a 0.9 electron volts per atom. And the atomic mass given 63.5 grams per mole, and density 8.4 grams per cubic centimeter. Calculate the equilibrium number of vacancies per cubic meter for copper at this temperature. So the first thing I need to do is find the number of atoms per cubic meter. So I can take my density, which is given as 60, that's not right, that's mass. There we go, 8.4. 8.4 grams per cubic centimeter. And then I'm going to turn that into meters. And I got to cube that. So now I've got grams per cubic meter. I can multiply by Avogadro's number, 6.02 times 10 to the 23rd atoms per mole. And then I can divide by the atomic mass, 63.5 grams per mole. So the grams will cancel, the moles will cancel, the centimeters will cancel, and I'm going to have atoms per cubic meter. So calculating that. I get 7.96 times 10 to the 28 atoms per cubic meter. Let me check that number. 10 squared to the third power is 10 to the 6. So I got 8.4 times 6.02 divided by 63.5. And that's going to be times 10 to the 6 times 10 to the 23rd would be 10 to the 29. So 7.96 times 10 to the 28. This is equal to n, the number of atoms in the per cubic meter. But we want the number of vacancies. We got to take that number. N is 7.96 times 10 to the 28 atoms per cubic meter. So that's this N. We're given Q sub V was 0.9, I believe. Electron volts per atom. T was 1273 Kelvin. And K, 8.62 times 10 to the negative 5. So N sub V, the number of vacancies per cubic meter, is equal to 7.96 times 10 to the 28. All of that times e to the negative 0.9 divided by 8.62 times 1273 times 10 to the negative 5. So that would be remembering to make this negative my when I'm this e to the this total here is negative 8.20. So I've got 7.96 times 10 to the 23rd e to the negative 8.20. I'm breaking this down by step just so that you can check and make sure you know how to do an exponent on your calculator. So e to the negative 8.2 should end up being equal to 2.74 times 10 to the negative 4. And so my number of vacancies per cubic meter is going to be 2.74 times 7.96. That's 21.8 times 10 to the 23 minus 4, 19, which is 2.18 times 10 to the negative 20. Okay? Oh, that's not right. Something's wrong there. 10 to the positive 20. That's it. It's got to be a big number. It's not going to be as big as the number of total atoms, but it should certainly not have a power that's negative. Okay, let's do another example. In this case, we are not given Q sub V. We're going to solve for it. And in order to do that, we're going to have to manipulate my equation. So I have that equation said N sub V is equal to N e to the minus Q sub V over KT. And I can rewrite that equation to say that the natural log of N sub V is equal to the natural log of N minus Q sub V over KT. In this format, it'll be much easier to solve for Q sub V. So I'm given temperature. I'm given the equal number of vacancies. I'm given N sub V. I'm given the atomic mass and the density from which I can get N. K is a constant, so I should be able to find Q sub V. So first let's get N. I've got a density for aluminum of 2.62 grams per cubic centimeter. And then I've got 10 to the 6 cubic centimeters per cubic meter. And then I've got Avogadro's number of atoms per mole. So my, let's see, oh, I still have to divide by the atomic mass, there it is. And that is 26.98 grams per mole. There we go. So now my grams will cancel, my centimeters cancel, and my moles cancel. And so I'm going to have an answer in atoms per cubic meter. So 2.62 times 6.02. My numerator is 15.77 times 10 to the 29. My denominator is 26.98. So I'm going to end up with n of being equal to 5.885 times 10 to the 28th. Latticytes or atoms per cubic meter. Okay, so I've got n. I don't seem to be able to back up on this PowerPoint. So I'm going to record these values. N is 5.85 times 10 to the 28. T is 773 Kelvin. And N sub V is given at 7.57 times 10 to the 23rd. And we're asked for Q. Okay, so next slide. So I know I'm going to use that form of the equation that becomes linear, and I'll write that again here. Natural log of n sub v is the natural log of n minus q sub v over kt. So the natural log n sub v is 7.57 times 10 to the 23rd is equal natural log of n, and I have for n 5.85 times 10 to the 28 minus q sub v, that's my unknown, divided by 8.62 times 10 to the negative 5 times 773. Adding 273 to the temperature in Celsius. So natural log of 7.57 times 10 to the 23rd is 54.98. And this is 66.24 minus q sub b divided by 0.0666. Okay, so Q sub B is going to be equal to 66.24 minus 54.98 times 0.0666. And so Q sub B is 0.75 electron volts per atom. And Q is usually between 1 and 3 electron volts per atom. Okay? All right, so I'm going to end this video here. We're about halfway through the topic, and then I'll pick up with a second video for the second part of the class.